I'm Moshe Vardi. I'm the ex-director of the Kennedy Institute. This is my new rank. And it gives me a distinct pleasure to welcome back home Sarita Adve, who is now the Cheng Professor in the Department of Computer Science at UIUC. She was at TICE 1993 till
99.
Till 99. And we're still sorry that she left. But she has done well, I must say. Everybody thought this is it for her, but she proved us wrong. She's done spectacularly well. She is an NCM fellow, an IEEE fellow, and even a nicer title, she's a woman of vision from the Anita Borg Institute and many other awards as well. She is here today as part of a lecture series. This is an annual the Ken Kennedy lecture that we hold here every fall. And we always invite the recipient of the Ken Kennedy Award. The Ken Kennedy Award is an award joined by ACM and IEEE in memory of Ken Kennedy. It's awarded annually and recognizes substantial contribution in programmability, in productivity, and computing, and substantial community service or mentoring contributions, modeled after what Ken Kennedy was, combining all three of these. And Sarita was recognized both for her research, in mostly focusing on memory models, which is going to tell us today about, but in addition for service to numerous computer science organizations and for exceptional mentoring. Let's welcome Sarita Adve.
Thank you. Thank you so much, Moshe, and thank you everybody for coming here. And I saw Don Johnson enter, and I saw Sydney enter, and I'm like, wow, made my trip. Well, I loved seeing you too, Benham. But you know what I mean. I have so many friends here. When I was asked who do I want to meet, I said just send an email out to ECE and CS and just see whoever signs up. There's just too many people here. Okay, so this is indeed like coming home for me. The title of my talk is Memory Consistency Models, They're Broken, and Why We Should Care. This is work that I've done with many colleagues over about 30 years, and I will highlight a few of them as I go along. So I would like to dedicate this award to the three institutions that I've been associated with: Wisconsin, Rice, and Illinois, as well as my community. So I've structured this talk in 4 parts, reflecting these various places. And I think of my time at Wisconsin as the time where I learned to question fundamentals. At Rice, I learned to believe in myself. At Illinois, it was learning that what real impact means is to change people's minds, and that takes time. And finally, it takes a village to do research, and all of us need to pay it forward. So I will talk about all of these things. Starting from Wisconsin a long time ago when I was a junior grad student, and I went to my advisor's office, Mark Hill, my mentor and a good friend, an amazing person. And he said, well, here are some papers on memory consistency models. And I'm like, what is a memory consistency model? Okay. So the first paper you read on this topic is by Lamport. He wrote this in 1979. The simplest memory consistency model is sequential consistency. And what this says is that the memory operations of a program execute in program order. Okay? And they execute one at a time in program order, and the net result is that you have an interleaving of these memory operations. So one single thread is executing its memory operations in program order, another one's executing its operations in program order, and the net result is the interleaving of all of these. Okay? And this is a really simple model. You talk to an undergraduate about what they might think of a memory model. This is what they would come up with, even though they wouldn't know the name. Okay, but it turns out that it's quite inefficient to implement. And so, at that time, there were many, many alternative memory models that were being proposed. And many of these came from the processor vendors. So these memory models were all about how do we make our implementations more efficient than sequential consistency, and what I refer to as the implementation-centric or hardware-centric view of the world. So the idea behind these memory models was, okay, let's talk about what order the memory operations of a single processor should execute in. Okay? And some of those models say, well, you know, if I have a store followed by a load, maybe I don't need to execute them in the order that the program prescribes. Maybe I can reorder them, and maybe nothing will change. So that would be a new memory model. And so if the programmer really wanted a store and a load to be done in program order, the programmer would have to insert something called a fence. Okay? So the idea was most of the time hardware is going to reorder stores and loads. That's going to give me good performance. And if the programmer wants the ordering, they go put in the fence. Okay? And there were many variations of this idea depending on what you wanted to reorder, where you want to put the fences, et cetera, et cetera. And different vendors had their own versions of these different models. So these models did provide good performance, but unfortunately, they're quite complex. Right? And many of them were ambiguous because this stuff turns out it's very hard to specify formally, and these were processor designers trying to specify these things. So you know, almost every day there would be a new memory model out there. Okay? All right, so this was the way things were, and almost every day I would go to Mark's office with my own new memory model. So then one day we sat and we said, well, what the heck is a memory consistency model, right? And really, it's very simple. A memory model is essentially an interface property that tells you what value a load in your program is allowed to return. And that's what it is, right? So what do I mean by that? So here is a simple multi-threaded program. There are two threads. Initially, X and Y and flag are all 0. Thread 1 is writing to X. It writes some value 26. Y writes to Y is 90. Flag equals 1. Thread 2 is waiting for flag to be 1, and then it reads X and Y. Okay, and if I ask, you know, my undergrad, the undergrads these days are too smart though. You know, the trick doesn't work anymore almost. But you know, about 10 years ago, we would ask an undergrad, you know, okay, what value should the read of X or Y return here? Okay, and most of them would say 90 and 26, right? That's probably what those of you who don't know this area probably think. But it turns out that in many machines today, X and Y might return 0. Okay? So the property of the system that tells me whether X and Y are allowed to return 0 or not, or whether they should return those updated values there, is what is the memory model. Okay, it's not did a store get reordered by a load, or did I put a fence here or not, right? It's give me the property that tells me what value these loads are going to return. All right? And this, of course, affects how you program. It, of course, affects the performance, and it affects the portability of my program as I move it from one machine to another. But most of all, the thing that Mark and I came up with was, this is really an interface property. This is really a hardware-software interface property. It affects programming. We need to take a far more software-centric view of this problem than was being taken at that time. Okay. And so we came up with this idea of the Dataracefree memory model. And the idea is really simple. All it says is, you know what, programmers want to reason about sequential consistency. The result that we saw earlier, the 96 and the 90 and 26 values being returned by X and Y, that's what a sequentially consistent machine would return. And that's what we should give the programmer. Okay? Just give them a view of the machine where every processor is doing its instructions, its loads and stores in program order, and the net effect is that there is some interleaving, which means what value is a load going to return? It's going to return the last value that was written to that memory location in this order. Okay, but again, the problem was that sequential consistency was inefficient. Well, so then the next insight was that for a certain class of programs that we refer to as Dataracefree programs, we can actually give sequential consistency with high performance. And the beautiful thing was the Dataracefree programs are also the style of programs that programmers typically want to write anyway. Okay? So the model said, if the programmer writes Dataracefree programs, we give them sequential consistency. If you don't write Dataracefree programs, I'm sorry, you didn't obey the contract. The programmer cannot rely on anything. All right, so just real quickly, what is a Dataracefree program? So here is the same multi-threaded program that I had before. And what we notice is that the writes to X and Y are what we would intuitively refer to as data operations. These are things that the programmer, that the process is writing data on. And the write of flag and the read of flag are what we would refer to intuitively as synchronization operations. These operations are being inserted by the programmer for the sole purpose of synchronizing these two threads. They're not really data accesses. Okay, so the key thing is that processors, hardware, compilers can reorder data accesses as much as they like, as long as at the synchronization points you restore order. It turns out that the result of the execution will be like a sequentially consistent execution. Okay? So then the key idea is that if the system could just figure out what is synchronization versus what is data, then it could go crazy at the data points, and at synchronization it would restore sanity. But this is an intuitive concept, what's data, what's synchronization? And so it turns out that synchronization accesses are those accesses which are involved in a race. And by race, I mean they could occur concurrently. So if you look at the reads and writes of flag, those are accesses that could occur concurrently. They could race. And so those accesses should never be called data. They should be called synchronization. And if we do that, hardware can give us optimizations, compilers can give us optimizations, and we give sequential consistency to the programmer. Okay, so that was a basic idea behind Dataracefree. It's a contract. Software tells us what's synchronization, what's data. Hardware and compiler do optimizations and give sequential consistency. This was great. Mark and I wrote a lot of papers with various collaborators, and I want to acknowledge Jim Goodman, Bart Miller, Rob Netzer, and Kurosh Karacharlu here. And of course, I graduated, right? And so this is where I come to Rice. I interview here. And this is why this award is so meaningful to me. My husband and I both interviewed that year. There weren't that many positions in computer science as we have today. And we had a two-body problem. And Ken Kennedy helped us convert, or he saw the two-body problem as a two-body opportunity. He hired Vikram in his group. I came to ECE as an assistant professor. Vikram reinvented himself as a compiler person. And for us, I mean, that was history. And I still remember the first day I saw Ken. He always seemed like he had this halo around him. I knew that he was famous for dependence analysis, auto-vectorization, data parallel languages, parallel performance analysis tools, and whatnot. At that time, I didn't know his service record. I didn't know everything he had done as a mentor. I found that out later, and I'll come to that later in the talk. But to receive an award in Ken's name is just, I'm just so deeply moved and so honored. It's hard for me to convey this. Anyway, so at Rice, I had two students who were who were just these most amazing students. Is the reason we are professors is to work with people like these, Vijay Pai and Partha Ranganathan. And at this point, I had really done mostly theoretical work. I had not really figured out what was really the performance benefit of these weaker memory models, of the Dataracefree style memory models. And so with Partha and Vijay, we did a lot of work trying to show the performance benefits of what were known as relaxed models. And in particular, there were new out-of-order processors emerging at that time. That was like, at that time, this was a big deal. New speculation techniques that affected how we did memory models. And there were no tools to understand the performance implications. So Partha, Vijay, and I, we built RSIM, which was the first publicly available multiprocess simulator with out-of-order processors. This work basically put us on the map, right? It showed that these models really, we can get good performance with these models even for these more complicated processors. Helped us build more confidence in Dataracefree model. And at that point, I realized that, okay, as hardware designers, we cannot, if we really want DRF to make an impact, we have to reach out to the languages and compiler community. We cannot continue this work just as hardware people. And so we wrote a paper in Proceedings of the IEEE. It was one of these papers that, there was nothing new in there. It was just a whole bunch of, just a retrospective of all the work we'd done. And Bill Pugh, who was at Maryland at that time, he read that paper. And he was working on the Java, he was looking at the Java memory model. Java had just come out. This was the first commercially successful multi-threaded language where parallelism was built as part of the language. It actually had a memory model, which is very different from all the other languages at that time. And he was looking at the Java memory model, and it seemed to have problems. He caught some problems, and he reached out to me, and he said, hey, do you want to work with us on this problem? We're trying to revise the Java memory model. Around this time is when I moved to Illinois. And for about 5 years, Bill Pugh, Jeremy Manson, Doug Lay, Hans Bohm, and several other people in the Java model expert group, and with a large community of people, we tried to solve the Java memory model problem. So interestingly, it took only a few days, maybe weeks, maybe a couple months, I don't know, I don't quite remember, but convincing this community that Dataracefree was the right foundation for the model was not hard at all, okay? So we did that. So that was great, right? Starting to have some impact. However, there was one really bad problem about Java, and that was that with the Dataracefree model, if a program has a data race in it, then all bets are off. That model does not give any reasonable semantics for racy programs. And Java as a language has this idea that it is a secure and safe language. So the whole concept that we cannot give any guarantees whatsoever for one class of programs, even if they are buggy programs and have races in them, just wouldn't fly for Java. You had to have some guarantees for all programs. At the same time, we could not have strong guarantees for racy programs because racy programs are known to be buggy programs or generally considered as buggy programs. And if we put too many guarantees for those, that would mean that we are most likely not doing the kinds of optimizations we want to do. Okay, so it would get in the way of performance. So there was this crazy tension. And here is a really crazy example problem that illustrates this tension. It's an unsolved problem even today. Okay, what is this problem? It has this very technical name of no out of thin air values. Okay. All right, so there are two threads here. The first one is initially x and y are 0. The first one is reading x and then writing the value it read to y. And the other thread is doing the exact opposite. And the question you have to answer is the outcome R1 equals R2 equals 42 an allowable outcome? What do you think? Should we allow this outcome or no? No, okay? So that's what most people would say because, well, where did 42 come from? It came from thin air, right? That's why it's called the out of thin air problem. How can you possibly allow such an outcome? How can any programmer reason about this program if it's going to give you the value 42? Well, so it turns out that if you think about processors that do speculation, and there are also compiler optimizations that can be brought to bear on this, you can have the following happen. Let's say that thread 1 speculates, okay, the processor predicts that x is 42. Okay, so it's predicting that and it's writing this to its register R1. And then it's saying, okay, x was 42, so now y is going to be 42, so it writes that to y. Thread 2 reads y as 42, and then it writes x as 42, and processor, and thread 1 says, aha, I told you x is 42, and so it justifies this speculation, right? So it's a self-fulfilling prophecy, self-justifying speculation. Okay. Now you would think this is crazy, and you would be right. Okay. Most hardware, or I don't know any hardware that does that. Okay. However, the problem is that it is incredibly hard to formalize a specification, okay, that prohibits this result without prohibiting common optimizations. Okay, so it would take me a whole talk's worth of material to really convince you about this in a deep technical sense. I'm asking you to take me on my word on this. We tried for about 5 years to deal with this problem, and we couldn't find a way to come up with a specification. Okay, no, go back on that. We came up with a specification finally. It passed the Java standard. It was so complicated, and we knew it was complicated, but we didn't have a choice, right? So you know, we knew this was crazy, right? But we had to do something. So in practice, the Java programmers are supposed to write Dataracefree programs, and you're fine. But if you want to reason about a buggy program and really write proofs about safety and security, then you have to worry about this complicated specification that I won't even show you. Sure enough, in a couple of years, so the Java standard got passed, right? We became famous for this and so on. But in like a few months or a year or so, somebody found a bug, which honestly wasn't surprising to me, and that specification still remains broken. Okay, and I'll come back to that in a bit. All right. So Java memory model is really Dataracefree plus a big mess. Okay, and that's the situation even today. Okay. So then Hans Bohm led, soon after that, led the effort to formalize the C++ memory model. And the C++ is a much more forgiving language than Java, because C++ already has undefined semantics for a whole bunch of stuff. Right? So you have a data race in your program, and you say your semantics are undefined. Okay, no big deal. Okay, so that's not a problem. So all right, this problem is solved. You know, what do I have to do with it? Hans is great. You know, you go through a standard, it'll be done. Okay, but there was a problem. Right? So again, Dataracefree was fine. We're going to use Dataracefree for C++. However, C++ is also a very performance sort of centric language, right? The whole you want to get high performance. Okay, and it turns out that there were some crazy parts of hardware that were, you know, industry hardware, commercial hardware that was mismatched to Dataracefree. Now, once people started looking at this closely, and this was related to the fact that the baseline Dataracefree model requires synchronization accesses to be done in order, and the synchronization has to be, you know, sequentially consistent. And because legacy hardware was not designed with this principal concept in mind, there were some things that made it harder to implement synchronization, sequential consistency on some commercially available hardware. And so it took another few years to talk to all these hardware vendors and software people and say, look, we don't have a choice. We just have to do this, right? We have to do Dataracefree because there is no other way by which we can come up with a formal specification, all right, that works, that will be palatable to programmers. Because if somebody gave us a formal, you know, some specification, and then we would go and show, well, yeah, but it doesn't work for this, and that reason. Okay, so that sort of went on for a while. Okay. But there existed hardware. There did exist hardware already where there was some performance penalty for Dataracefree, and so we came up with a compromise where, again, the baseline was Dataracefree, but for people who wanted the highest possible crazy performance, they had the option to use this thing called relaxed atomics. And Hans and I gave several talks that said, well, only experts should be using these relaxed atomics. You know, you shouldn't even be teaching this to undergraduates. Nobody should be using this unless they really know what they're doing. So in other words, it was Dataracefree plus a big mess, because soon there was a hole discovered in relaxed atomics as well. And again, C++, this problem remains unsolved. Okay? Still, good news was after about 20 years of work since I did my thesis, we had convergence at last in the sense that Dataracefree was accepted as a baseline foundational model for the most common languages at that time, and the basics were converged. Okay, but there's still open problems. How do you debug RACI programs? How do you avoid out of thin air values if you care about safety, security, etc.? No semantics for relaxed atomics. In fact, and then Hans and I wrote this paper in CSCM. I think Moshe pushed us to write this, and this was about memory models, a case for rethinking parallel languages and hardware, and this puts together all of these thoughts that I've been talking about. So this was still a few years ago. And this is the situation today. The C++ manual today, okay, if you open it and you look at the specification for relaxed atomics, it says this. It says these are races that don't order other accesses. Implementations should ensure no out of thin air values are computed that circularly depend on their own computation. I challenge any of you to apply this to a piece of code and tell me whether the code obeys this or not. Okay, this is like just few words strung together. Okay, and my students and I, we were working on trying to make this better, and somebody at some famous major research lab, a PhD, sends my student this message saying, C++ relaxed atomics were the worst idea ever. I just spent days and days trying to get something to work. My example only has 2 addresses and 4 accesses. It shouldn't be this hard. Can you please help? This is a PhD, okay, in computer architecture, very, very smart person. Okay, so this is where we are, all right? So what have I been doing since the last decade? So things are broken, okay, and we took a step back and we said, well, let's get back to fundamentals again, all right? Let's ask again. Think about things from scratch. So from about 2008 to about 2014, with Vikram Adve and Bin Choi, Rakesh, Matt, and Hyojin, who were my former students, we said, we've been thinking about software-centric view of consistency, cache coherence protocols are a key part of the implementation. We have so many problems happening because of implementation issues. Let's think about what it really means to be coherent in a more fundamental way. Let's think about hardware from scratch, and let's see where we go. Okay, let's take a software-centric view of coherence. Lucky for me, Vikram at that time was working on a language called deterministic parallel Java that was about using a type system to get determinism, and long story short, we were talking about it and I was like, oh my gosh, if all languages were like that, it would solve my memory model problem, okay? And so I said, let's assume all languages would be like this, okay? With a strong type system, deterministic languages, and I said, now let us think about how would we design the Coherence Protocol if the world changed, okay? And of course, we knew the world wasn't going to change, but it helped us think about the fundamentals. It helped us think about what a coherence protocol really means. And so we identified the fundamental minimal coherence mechanisms. And then once we'd done that and studied this as part of the DeNovo project, we realized that what we had was a more performance energy efficient and less complex system than the standard coherence protocols of the day, which are called MESI or MESI. And then we loosened the software constraints, made these ideas more palatable, more usable for general programs, and we had a great system, right? So we thought, okay, awesome. All right, we know now what is the minimal hardware, what is the most efficient hardware, and here I want to acknowledge Mark Sneer and our parallel research center by Intel and Microsoft that really motivated and let us create this team of people that could solve this problem. Okay, the problem with that approach though was it was still a clean slate approach, and to do a clean slate approach means it's really, really hard to get buy-in from the Intels and the IBMs, et cetera, of the world. They've been doing coherence the way they've been doing for like, since before I was born. And, no, that's not quite true, but almost. And so, I wasn't going to be able to change their minds. I'd barely changed their minds for consistency. It wasn't going to happen for coherence. But lucky for us, the hardware world is changing around us, right? The end of Dennard scaling and Moore's law means that the way we do architecture has changed, okay? Architecture is getting more, there's more application specialized accelerators we're using, we're building heterogeneous systems, and if you heard Hennessy and Patterson's Turing Award lecture 2 years ago, they talk about how architecture is entering this golden age. Awesome, right? Very excited. Golden age, clean slate designs are going to work. But all that did was give me a sense of deja vu. And we seem to be back to doing the same, repeating the same mistakes for coherence and consistency. So let me tell you a little bit about this next phase of my work that that I've been doing with now some of them are my former students and the others are current students. We really hope that this work will make an impact. But I want to take you first through the deja vu phase of this work to give you a sense of how hard this problem is. Okay, so the golden age of specialization and heterogeneity is here. On the left, on your left there is a dial photo of an iPhone, and on your right is over a period of time, the number of accelerators on the y-axis, okay, that are present in an iPhone. Okay, and this is courtesy of my colleagues David Brooks and Guyon Wei at Harvard. So what this is showing is that the number of heterogeneous devices, accelerators, is exploding on our chips, and it's just going to keep increasing because specialization is the one hammer that we have to get more energy efficiency, given that Moore's law and Dennard scaling are more or less dead. Okay. So that's great that specialization gives us energy efficiency. The problem, though, is we don't know how to put all these specialized systems together in a real system. We don't know how to program them. And so that's what I'm trying to do now. And the next few slides, I'm going to talk about how specialization needs better memory systems, okay, and what that means to the memory model and so on. All right. So with traditional heterogeneity, okay, with current systems, you can have a CPU and one accelerator, let's say. And a typical way of doing a heterogeneous program is that the CPU will invoke a computation on the accelerator. Now it has to create the data for that accelerator, and so it has its own memory. It takes the data from its own memory, copies it explicitly into the accelerator memory. The accelerator then does the computation on this memory, finishes the computation, creates new data, sends it explicitly to the CPU. There's lots of back and forth of data movement going on. This needs to happen in bulk because it's slow. And so there's wasteful data movement. There's no fine-grained synchronization. If you have irregular access patterns, it's hard to do here because the data movement is in bulk. Okay. And so industry has now begun to recognize this, and industry is now moving towards a vision of coherent shared memory, where the CPU and the accelerators all have one common address space. It's coherent, and this allows us to do implicit data reuse, fine-grained synchronization, and irregular access. Okay, so if every life is so good, why am I giving this talk? Well, of course, it's not so good because the current solutions are quite complex and quite inflexible. Now, what do I mean by that? Okay. So the CPU coherence protocol. So one of the problems with current solutions, this goes back to the deja vu comment, is that even though we've entered this golden age, a lot of the solutions that industry is adopting are taken from our experiences with CPU land. Okay? And so all the complexity we have there seems to be coming in here. So let me give you a little bit more detail of what a CPU protocol CPU cache coherence protocol looks like and the implication of that. Okay, so the key thing about a cache coherence protocol is this invariant of a single write or multiple reader. And the idea is that when you have a cache miss, okay, if you have a write miss, the writer has to go and get ownership for the data and invalidate all of the readers, okay, all of the sharers. And if you have a read miss, you add yourself to the sharer list. You don't, you know, for those of you who know this, you know it. If for those who don't, it's fine. You don't really need to understand the details. The point is that this incurs a lot of complexity. You need to have a directory to store the sharer list. There are many transient states in these protocols. There's excessive traffic, indirection, lots of waste. It's complex and inefficient, but it works really well on a CPU. Okay. So then the GPUs came along, all right, and realized that, you know, all the CPU stuff is just way, way, way too complex. So the early GPUs, the baseline GPUs that we have, do something very simple, like super simple. All right. What they do is they realize the Dataracefree model, okay, is what we want to maintain. And with this model, since there are no data races, they realize that at synchronization points you can do, you know, interesting stuff, and the data accesses can go quickly, right? That was the idea of Dataracefree and CPU land. However, what they do is something very, very heavyweight at synchronization. So they flush all the dirty data at the synchronization, unnecessary write-throughs, and at every synchronization they invalidate the entire cache, all right? So a synchronization access becomes this really heavyweight thing where the entire cache is invalidated, there's no data reuse across this, plus the synchronization accesses have to go all the way down through the memory hierarchy to get done. What this does is makes synchronization simple but quite inefficient. And this was actually fine in the days when GPUs were used for graphics and for you know, very coarse-grained compute. Now, as we want to use GPUs for more interesting applications, this has become a big hammer, right? This is a big problem. Okay, this is where deja vu comes in. So what was the solution to this problem? Guess what was the solution to this problem? We changed the memory model. Okay, we make the memory model more complex. Okay, so AMD's memory model and effectively NVIDIA's memory model, they do the following. They replace Dataracefree with something called heterogeneous race-free. And the idea here is that you still are not required to have data races. You're required to have no data races, but now they introduce the concept of heterogeneous data races. What is a heterogeneous data race? Well, I'm not going to get into details, but the idea is it really depends on your memory hierarchy. Okay, so if you have a data race between threads that are in the same cache domain, something like that, all right, then it's not a heterogeneous race. If they are in between different domains, it's a heterogeneous race. But what that means is now the programmer needs to be aware of the memory hierarchy of the system. Okay, and so they introduce a notion of scopes, and again, the details are not important, but what I want to get across is that again, we are at a point where to deal with the hardware, we have exported that complexity to the software. Okay, just because we want hardware optimizations. And so, so they have these different scopes where, you know, if you say that something is a local scope, you're very efficient. If it's a global scope, you're not efficient. And so the idea is that the programmer should find, you know, identify local scopes. But to identify local scopes, you need to know the hardware, et cetera, et cetera. Okay, so higher programming complexity. And so what we did in the last few years is ask the question, okay, you know, do GPU memory models really, really need to be more complex than CPU models? I mean, CPU models are already complex. Dataracefree is as simple as we could get it to be, but it's still complex. And so then we showed that no, GPU models don't have to be so complex if coherence is done right. So going back again to thinking about things from the fundamentals, and we brought to bear all our experience with the DeNovo protocol, which was really not designed for this world in mind, but showed that if you use DeNovo and DRF, you could get the efficiency and the simplicity of the GPU implementations and the simpler memory model, and life would be good. Okay, so we put this all together in a way by which we essentially identified what are the fundamental traits of coherence protocols. If you look at most textbooks today, you will find that they say a coherence protocol means MESI, single writer, multiple reader, etc. For us, a coherence protocol is, again, the property that tells you, that allows you to return the read that the memory consistency model wants. And from that point of view, there are two things that a coherence protocol needs to deal with. The first is when you have a read hits in your cache, you want to make sure it's not returning stale data. And if the read misses in your cache, you want to make sure you can go and find where the up-to-date data is. And these are the only two things that a coherence protocol needs to do. Okay? Once you figure that, once we've identified that these are the fundamental traits, okay, these are the fundamental axes, then we can come up with implementation mechanisms that do these two things in different ways. Okay? And so for invalidating stale data, then it becomes clear that, okay, you can have writers invalidating stale data or readers taking responsibility themselves. And for tracking up-to-date copies, you can have ownership base or you can have write-through base. And once you put this all together, then it turns out that what the CPU style things do is they're writer-initiated invalidations and ownership base. What the GPU style systems do is they're reader-initiated invalidation and write-through base. And what DeNovo did, the reason it's so successful is that it does reader-initiated invalidations and it gets ownership for written data. So it's a different part in this space and it's a sweet spot. Okay, and so we did a whole bunch of evaluations and showed, DeNovo does better and, 50% lower energy and 25% better performance, et cetera, and pretty much answered the question. And in fact, the authors of AMD who did the HRF model, the more complex model, they then wrote a paper that said, yes, DRF is, HRF complexity is unnecessary. You can do DRF if you do coherence right, and they had their own tweaks and so on. So that was great, okay? And we got a lot of buy-in, okay, that DeNovo plus DRF is an efficient and simpler memory model. Okay. So that's good. However, again, the problem here, the next problem is that in a heterogeneous system, right, you have the CPU, you have a GPU, you have other accelerators, okay? And, as I said before, it's going to be really hard for the CPU folks to go to DeNovo. It's just not happening, all right? They just are too ingrained. And so then we also ask the question, and you know what? These heterogeneous systems are all about specialization. We want them to have flexibility so that they can do whatever styles of communication we want, and coherence just sort of works accordingly. We want to have specialized coherence. And so then the last couple of years, what we've been working on is recognizing that heterogeneous systems have diverse memory demands, and we would like to have an interface that can deal with all of these memory demands. So existing solutions, what do? Existing solutions, they say, okay, CPUs, you do this messy style coherence. Accelerator one, if it's a GPU, you have this GPU style coherence. People who like us might do DeNovo style coherence, and so on. But when you put these all in the same system, then what happens? Well, when you put all of them in the same system, we still resort back to a messy style complicated coherence protocol at the last level. And when we integrate all of these accelerators together, we give up a lot because we are using this messy coherence. So in some cases, you don't even allow the accelerator to have coherence. In other cases, you might replace the accelerator's coherence with messy style. And in other cases, you put in another level of cache to filter, to act as an intermediary, and that creates more latency. And so what we've been doing lately is Spandex, which is a new flexible accelerator coherence interface. And I don't have time to give you the details of Spandex, but the idea is that Spandex essentially adapts to exploit individual devices' workload attributes, and it does that again by identifying an interface that has these fundamental properties of what I described. It looks at things more fundamentally in terms of what are the who's going to invalidate stale data, who's going to write, and so on and so forth. And we've shown results that it has better performance and lower complexity, fits like a glove for each device. I think I'm going to fast forward a little bit. So what we are after, again, is an accelerator communication interface. We believe Spandex is a big part of the answer. We are working with some industry colleagues to see how far we can push this. We've also made a lot of progress in the relaxed atomics domain, but the key is that we still believe Dataracefree is the right memory model, and these coherence protocols fit very nicely with the Dataracefree memory model. We're also looking at handling approximations and solution quality within this interface. But I do want to spend just one slide on what about software, right? So this is, so far I've told you about the coherence protocol, hardware, et cetera, working with Dataracefree. But now that we've started to use coherence specialization, there's a lot going on here. How do we abstract that all out to the software? What is the hardware-software interface? And this is a project that I'm working with Vikram. Vikram's leading this project, as well as with Sasha Misailovich, another colleague at Illinois, where we are developing this idea of a hardware-software interface that we call the heterogeneous parallel virtual machine. Those of you who are familiar with LLVM, think about it as what's the next version of LLVM for heterogeneous computing. And the goal here is that the hardware abstraction that is presented to the compiler and the programmer has parallelism as first order, has communication as first order, and essentially we describe this hardware-software abstraction in terms of a hierarchical data flow graph. Okay, so again, thinking about this in terms of fundamentals, and we've shown how we can use the same abstraction to target code to GPUs, CPUs with vector extensions, some domain-specific accelerators. We're working on FPGAs. So that's our sort of approach, work in progress, for where we think the hardware-software interface should be going. And looking forward, I believe that we're going to have a lot of domain-specific languages at the top, a lot of hardware innovation at the bottom, and this in-between layer is going to be key. And we think HPVM, Spandex, and DRF consistency is going to have a big role to play. We continue to work on these things. So that's the technical part of my talk. I want to come back to Ken. All right. So, as I said, I do want to talk a little bit about our community and paying it forward. As you can see, all this work that I did, there's so many people involved, lots and lots of collaborations over 3 decades, lots of mentors. Sydney here, I mean, the reason I'm so delighted to see you is because I will say this, another quote from you. One day you came to me, things weren't going very well for me actually in the first couple years at Rice, and you came to me and you said, I know you're going to be successful. The question I have for you is, what kind of success is it going to be? So this is the kind of mentor I had at Rice, and I mean, I have so many such stories, right? And the only thing I can do is to pay it forward, okay? And I want to leave this message really strongly with all of you, that this is something each one of us needs to be aware of. Nobody here is successful without the help of a lot of other people. And Ken is a great, great example of this. I mean, the number of people he's helped, the service he's done, or he did, is absolutely mind-boggling. And again, to receive an award in his name on this account, on the service and mentoring account, also means a lot to me. Okay, so I want to say a little bit about what I've done in this space, because the award did recognize this work as well. So Moshe, the award says numerous service to numerous organizations, but really I think my most important service was as SIGARC chair. I was chair of SIGARC, ACM SIGARC for 4 years. I just stepped down a few months ago. This is my executive committee, just an incredibly amazing group of people. There is no way we could have done whatever we did without them. The part that we did a lot of work. The part that I want to talk about, highlight, is our work for diversity and inclusion. And this was a community effort. I happened to be SIGARC chair at the time, great committee, and amazing colleagues. Natalie and Wright-Jerger, Kim Hazelwood, Margaret Martinozzi, Catherine McKinley. We worked together with the community to do some of the things I'm going to talk about. No talk on diversity and inclusion, no technical talk, no mentoring talk, no service talk in my field of research would be complete without the mention of Janie Irwin. She also happens to be the person who nominated me. I did not know she nominated me. She's retired. This is what she does in her retirement. She nominates people for awards without even telling them, and so I did no work really to get this award. Anyway, so here are some key events in the last 2 years in my community. So a couple years ago, my colleagues Natalie and Wright-Jerger and Kim Hazelwood, they did a study and published it in the SIGARC blog, which I highly recommend everybody subscribe to. It's great. The study really put a flashlight on the gender ratios in our community. Okay, so it showed the number of keynotes, PC chairs, awards. I mean, the numbers were just this small when it came to gender. Okay, all conferences needed to improve, but one in particular stood out. And that conference celebrated its 50th anniversary in that year, and had a panel called Legends of Micro Panel, which was all white, all male. That sort of became a big flashpoint. And my colleague Margaret Martinozzi, she read at that panel a statement, a diversity statement that was essentially a call to action, okay, with the support of a lot of people. A call to action, and it was a clear public support for change. And so SIGARC put out, we said we're going to work for diversity. This, we have been working for diversity, but this study and all of these events were a big wake-up call, and so this became a front and center thing in our community. We did there was another blog piece that talked about diversity in conference governance. Steering committees, they were not just gender-based diversity, but diversity on institutions, academic lineage, etc. And then this other blog piece really sort of went viral. You may have read it. Catherine McKinley wrote this piece on personal accounts of harassment. Many people, including me, we were shocked that sexual harassment actually happened in our conferences. This was something that it was just a shock. But then I actually talked to people to whom this happened, and Catherine wrote a blog piece with anonymized names, but people who provided first-hand information. And this was a real wake-up call. So one of the things that I'm really proud of that we did was worked very closely with ACM and created SIGARC Cares. This is a committee that helps targets of harassment. It serves as a sounding board to people. They can come and talk to CARES members at conferences and get help in figuring out what to do, how to report to ACM, et cetera, et cetera. Very soon, Margaret Martinozzi and Catherine McKinley are the founding co-chairs. They've done a fabulous job on this. SIGMicro joined CARES, and now CARES it's blessed by ACM. So all of these conversations affected ACM's harassment policy. ACM came up with a new policy that has words that came directly from these conversations. And now there are many SIGs that have CARES. So SIGGRAPH has, there's SIGGRAPH CARES, there's SIGCOM CARES. SIGPlan is going to roll out CARES. And if this weren't a problem in our community, we wouldn't be having all of these committees, right? And so I encourage you to go to the SIGARC Cares website and see what we're doing and try and emulate this in your communities. We also have my colleague Natalie Enright-Jerger. She spearheads the Women in Computer Architectures group. This is now an official subcommittee of SIGART, so we put resources in it. This is our central place for making diversity-related decisions. And please visit this website. It's an amazing web portal. It has a directory of women in computer architecture. Nobody today can say, I don't know who to nominate, which women to nominate for an award in architecture because I don't know the women. Okay, so they're there with very nice descriptions, and occasionally we run profiles of these women. And there is a Slack mentoring channel. It's just providing support to women. We did VicArc did a graduating women brochure. Hopefully some of you saw that. That was a big hit with universities. There's just tons of things that this group does, and I highly, highly recommend that those of you who are in different communities and don't have similar things, please take this message back to your community. So get data, raise awareness, fix problems. And for those of you who might say, oh, but this is not a problem in my community, honestly, I felt the same way. Okay, until all this data was published, and until I always knew there weren't enough women, right? I mean, that's not hard to see, but why are there not enough women? It was an eye-opening exercise. Okay, so there is a lot that we can all do, and I hope you will go ahead and do it. And I want to thank my family, that's Vikram and my kids, and wrap up with this. All right.
I know we ran a little bit late, but we have to take a few questions. So, Moshe.
You talked about the hardware. You talked about the software. You didn't talk about the programmers.
Uh-huh.
I think this is a very important part of the equations.
Yeah.
I think partly what happened is the same way that the hardware people neglect the software, I still feel we're neglecting the programmer.
Yeah.
And part of the question at the end of the day is, do we have some studies? For example, I told you that I believe that people completely avoid these memory models. But I must admit, I mean, it's based on a conversation with 3 people. So it is not a very, very sound, it is sound but not complete in my terminology. Will be really useful. And today we actually have lots of software repository. There's a lot of work on software mining. Will be really good to start to get some sense, okay, what really happens when real people, real programmers, not the expert in the companies writing specialized benchmarks. Real people write real software. What really happened? How do people use memory models? I think we're missing this part of the equation. Yeah.
No, that's actually a really, really good question. And in fact, today with the explosion of domain-specific programming languages, for example, right? I think, Moshe, we still are struggling to ask the question about, for those programming languages, how is even the memory model represented, right? So in many cases, there's not even a part of this, it's not even part of the specification. You're exactly right. You're exactly right that we need to ask how programmers are using memory models. But I feel there's lack of understanding across the whole stack. There's still a lot of understanding to be done across the whole stack. In fact, our work on the relaxed atomics problem that, I didn't get time to talk about that. The place where we started was to reach out to developers and get all the codes that they were using for these relaxed atomics. The whole inside of that ISCA paper that we have on what we think is the right solution to relaxed atomics was the observation that all these programmers, they're using these relaxed atomics in a very small number of patterns, okay? And so our insight was, and this is like a Band-Aid patch, but the insight is related to what you're saying. That for those small number of patterns, we can actually extract them out, abstract them in a way, and get rid of this problem. Yes, it's not a general solution, but this is what they're using, right? Now, these are still the developers who are the performance developers. It's not what you're saying. All I'm saying is that we're getting there, right? We're trying to anchor this in real life, okay? Yeah.
Thank you for the talk, excellent. So a 2-part question. As a security person, I'm all the buzz on speculation side channels. But it occurs to me that you might be able to model them with relaxed memory models or any memory model, and is that a solution?
Yeah, so it's actually, we should talk about this offline, but I think there's a lot of work right now on dealing with these side channels with what I call, what I used to call hardware-centric, implementation-centric things. So, I'm going to use these fences and those fences to get rid of side channels, et cetera, et cetera. And my view really is that we need to lift this problem at the hardware-software interface level, right? I believe that some of the insights we've had here apply there, and I so badly want to work on that problem, but darn, there are only 24 hours in a day. Yeah.
Any other questions? If not, we do have a reception outside. If you're too shy to ask your questions, Sarita will be here.
Yeah.
Let's join me in thanking Sarita again.